You can see everything and still be late.
That phrase, it sounds like a riddle, doesn't it? But it's probably the most accurate summary of elite performance we've found.
It's the perfect hook for what we're about to unpack today. When we talk about the ARES performance loop, anticipate, route, execute, sustain, and our fruit is, well, it's arguably the most complex.
And it's definitely the most invisible part of the process. This is where performance is won or lost based on how well your brain manages data, not how fast your body moves.
So in this deep dive, we're getting into the architecture of the brain's high-speed decision network. We're not talking about just raw sensory input. We're talking about what your brain does with that input.
Right. What happens in those critical milliseconds after the light hits your eye, but before your muscle even gets the command to fire?
And the sources we've got give us a really precise blueprint for this. We're talking about circuits and pathways that operate faster than you can even think.
Our mission here is to really understand the neuroscience of this signal management. So scientifically, we define root R as the brain's entire signal management process.
Okay, so what does that actually mean?
It's the filtering, the prioritizing, the predicting, and finally delivering a clean, high-speed signal for action.
It's the fundamental bottleneck.
It is the bottleneck. If you want to move faster, you have to route signals faster. It's that simple.
Okay, let's unpack this then. Start with the physical architecture. This whole journey starts with light hitting the retina, but where does the routing officially begin?
Well, the process initiates at the retina, where light gets converted into electrical impulses. But right after that, this massive stream of information travels up the optic nerve and hits its first major checkpoint in the midbrain,
The thalamus.
specifically the lateral geniculate nucleus, or LGN.
Right, and the LGN is so much more than just a simple relay station. If the retina is the camera sensor, then the LGN is like a high-speed sorting facility.
That's a perfect analogy. It's critical because this is the first point where the system starts to segregate this flood of sensory input into separate parallel streams. The whole success of rapid routing depends on what happens right here.
So let's talk about those screens, because this is where speed and detail start to get separated, right?
Exactly. The LGN splits the information into two main pathways. We call them the magnocellular pathway, or M pathway, and the parvocellular, or P pathway.
M pathway. That sounds fast.
It is. The magnocellular stream is built for speed. It uses large, fast-conducting neurons. It's all about motion, flicker, high contrast changes, the dynamic stuff.
So for an athlete facing a fastball, this is the high-speed lane.
It's the express lane. Think of it like a low-resolution but very high frame rate video feed. It prioritizes timing and speed over everything else.
And the P pathway. That's the scenic route.
That's right. The P pathway uses smaller, slower cells. It's specialized for fine detail, for color. It's what helps you see the seams on the baseball.
What you're seeing.
Precisely. It helps you know what you're seeing, but it's structurally slower. In a high-speed situation, you can't afford to get bogged down in that stream.
So right at the first step, milliseconds are being won or lost based on which pathway gets prioritized. Okay, so after the LGN, the signals hit the visual cortex, V1, and the system splits again.
Yes, and this is the big computational split. This is where the brain starts deciding what you need to do with the information. The data bifurcates into the ventral stream and the dorsal stream.
The famous dual stream system. Let's use the nicknames here for clarity. The what stream and the warehouse stream. So the ventral stream.
The ventral stream runs through the lower temporal parts of the brain. It's heavily fed by that slower P pathway we mentioned.
So this is for conscious object recognition.
Yes. Form, color, memory. It's all about high-resolution identification, knowing what an object is.
And this brings us to the pathway that really matters for an elite athlete in the heat of the moment.
The dorsal warehouse stream. This pathway runs through the upper parietal regions, and it's fed by that fast M pathway. This is the brain's action stream.
This is what turns seeing into doing.
Exactly. It's about motion, spatial guidance, and crucially, transforming visual data directly into motor commands, often completely outside of your conscious awareness. It tells you where something is and how to interact with it.
So this explains why so much of elite performance feels unconscious. The athlete isn't consciously analyzing the details. They're bypassing the what stream and letting the dorsal stream drive the action directly.
That's the highest evidence we have for why seeing is different from acting. You can know what you're looking at, but if that signal isn't routed correctly through the dorsal stream, you can't interact with it. The action command fails.
Okay, so if you have this fire hose of data splitting into all these different streams, the system would just overload without some kind of massive filtering system.
Yeah.
Routing success isn't just about speed, it's about filtration.
100%. You need massive, continuous noise reduction. The key mechanism for this is called input gain control.
Input gain control, break that down.
It's about suppressing predictable noise to amplify only the signals that matter for what you're doing right now. And this starts right in V1, the primary visual cortex, with a mechanism called surround suppression.
Surround suppression. It sounds like a noise cancellation algorithm for your eyes.
That's a great way to think about it. Basically, a neuron in V1 fires strongly when a stimulus is in the center of its receptive field. But if that same stimulus also fills the area around it, the neuron's response is actually suppressed.
Wait, that seems backwards. Why would more stimulus lead to less signal?
It's all about efficiency. The brain is saying if the context around the signal is predictable and unchanging, like a wall of fans, then we don't need to waste resources processing it at full volume. It reduces redundancy.
So it's designed to make change and novelty just pop.
Precisely. It prioritizes the error signals, the things that don't match the background. This is what allows a hockey puck to pop out against the ice, neurally speaking.
But something has to be telling V1 what's relevant and what's predictable. That sounds like it requires top-down control.
It does. And that control comes from your prefrontal executive, signals your goals. These signals control the sensory flow through a process called thalamic gating.
This is where attention becomes a physical filter.
Absolutely. The cortex essentially tells the thalamus via a structure called the TRN which data packets to prioritize and which to drop. It acts like a firewall administrator for your senses.
So it filters the noise out before it can even get up to the higher processing centers.
Exactly. Routing success is defined by how well an athlete can maintain that attentional filter under pressure. The whole system is designed to accelerate action, not by processing everything, but by strategically ignoring almost everything.
Which brings us directly to the cognitive side of this prediction. We've mapped the hardware, now let's talk about the software that makes it all run so efficiently.
Right, and this is where we get into predictive coding theory. The idea that the brain isn't passive, it's constantly generating its own models, its own predictions about what sensory data should look like.
It's placing bets on reality before reality even arrives.
Exactly. And the efficiency comes from how it handles the difference between its prediction and what actually happens. It suppresses signals that match the prediction. It doesn't need to waste energy on things it already knows.
So it only sends the errors up the chain.
Precisely, the prediction errors. If a pitch follows the exact trajectory the brain predicted, there's very little signal. If it breaks unexpectedly, that massive prediction error is the only thing that gets fast-tracked up the system to update the model and change the action.
This explains what we see as neural efficiency. Elite athletes literally use less brain energy to do the same task.
Because their predictive models are so much better, they reduce the uncertainty earlier in the process. It's like driving a familiar route. You do it faster with less cognitive load. Lower error means faster routing.
But this entire system is incredibly fragile. Under high pressure or fatigue, performance just crumbles. Why does that cognitive load cause what you call routing overload?
Because that load directly taxes the control centers, the frontoparietal attention network. That network is responsible for top-down attention and suppressing distractors. When it gets overloaded, the filter fails.
The firewall comes down.
Exactly. The brain loses its ability to selectively filter. The system gets flooded with noise. The athlete is technically seeing more, but the relevant signal gets lost in the static.
And that overload has a catastrophic effect on the final gatekeeper of action.
Visuomotor gating. This is the last step, orchestrated by the basal ganglia. This is the structure that makes the rapid go or no-go decision.
This is where potential action becomes committed action. This is where choking becomes a scientific phenomenon.
Right. The basal ganglia has to balance a go pathway that initiates movement and a no-go pathway that inhibits all other competing movements. High-speed action requires a very strong go signal and an equally strong no-go for everything else.
So when routing overload happens, that balance breaks down.
The system gets flooded with conflicting signals. The basal ganglia doesn't get one clean go command. It gets, say, 5 competing ones. The system either fires the wrong action or it just hesitates. It becomes paralyzed by choice.
And that paralysis, that hesitation,
Yeah.
That's what we see on the field and called choking.
And that's the key takeaway here. Choking isn't a failure of character. It's very often a measurable physiological failure of this routing process. It's routing overload. The brain's circuits can't maintain the filter needed to make a clean action selection.
That completely reframes the conversation around performing under pressure. It's not about being mentally tough. It's about the physiological integrity of these neural circuits.
Exactly.
Okay, let's make this tangible. Let's translate these failure modes into real sports scenarios so you, the listener, can see how this actually looks.
Yeah, we can look at a few really distinct failure modes.
Let's start with a quarterback. He's reading the coverage, he sees the whole field, but he's late on the throw or picks the wrong target. A classic wrong priority issue. Where is the routing failing?
The failure there is in the top-down control from the frontoparietal network. His ventral stream, the what stream, is fine. He sees the helmets, he sees the jerseys, he knows what he's looking at.
But the clock is ticking, and he needs to pick one location right now.
Right. And the frontoparietal network is supposed to overlay a priority map on that scene. It should be amplifying the signal from the open receiver and aggressively suppressing the signals from all the defenders.
But under pressure, that suppression fails.
It fails. So instead of one clean, high-priority target being routed to the basal ganglia for action, it gets 5 messy, competing signals. And the result is hesitation, a late throw, or a bad decision. It's not that he didn't see the open man.
It's that his brain couldn't prioritize the open man's signal above the noise. Okay, next up. A baseball hitter picking up release cues. This is all about high-speed motion processing. If a hitter is consistently late, what part of the pathway is lagging?
This is a classic inefficiency in the fast M pathway and the dorsal stream, specifically in a motion-sensitive area called MT. Area MT is the brain's motion calculator. It's figuring out trajectory and speed in real time.
And any micro delay there throws the whole swing off.
It does. And we can actually measure this. The science shows a direct link between reaction speed and something called the N2 latency in area MT.
The N2 latency.
It's a marker for how fast the brain initially processes visual motion, and the research is clear. Elite performers have a significantly faster, a lower N2 latency. They are literally routing the motion signal earlier in time.
So a slow N2 latency means the hitter's perception of the ball's motion is delayed before the signal even fully forms.
That's it. The delay isn't in the muscles. It's measurable in milliseconds in the brain's core motion processing centers.
Okay, last one. A hockey goalie tracking a deflected puck through traffic. They see the puck, but the reach is off. They overshoot or undershoot. This sounds like a reference frame error.
It is. This is a breakdown at the highest level of spatial routing in the posterior parietal cortex, or PPC. This is where the brain integrates everything. What your eyes see, your sense of balance, where your limbs are in space.
It's the brain's GPS, constantly recalibrating.
It has to perform what's called a sensorimotor transformation. It takes the eye-centered visual data and translates it into a body-centered command for your hand to move accurately.
So if that transformation process is disrupted by cognitive load,
the command is flawed. The goalie sees the puck just fine, but the movement trajectory the brain calculates for the glove save is spatially misjudged relative to the body.
the routing failed at the very last step, the action phase.
And what's powerful is that all these examples, the late throw, the slow swing, the misjudged save, they look like physical errors, but they're not. They're specific, measurable failures in the neural routing architecture. The problem is in the data pipeline.
So this entire system, the filtering, the predicting, the action selection, this is exactly what the errors quotient is measuring with AQR.
That's right. The AQR metric is designed to quantify the efficiency of this whole signal management system under the toughest conditions: speed, distraction, and cognitive load. It goes way beyond simple reaction time. It measures computational speed.
So an athlete comes in and we can establish a baseline. Their AQR might be insert baseline, which shows us where the milliseconds are being lost.
And after targeted training that addresses that specific bottleneck, the slow N2 latency, for instance, we reassess. We see a quantifiable jump in efficiency to an AQR score like insert improved.
And that jump is the direct evidence that milliseconds matter.
It confirms the training worked at a neural level.
And that data-driven loop is the core of the errors method. It's not just generic training. It's a precision attack on an athlete's unique bottleneck.
It's a 5-step sequence. It's very specific.
Step 1, assess. We get the baseline AQ score, a diagnostic snapshot.
Step 2, identify the bottleneck. We use the AQR data to pinpoint the failure. Is it filtering? Is it gating? Is it prediction? We find where the system is bleeding time.
Step 3. Train progressively. We apply targeted exercises to strengthen that specific circuit.
Step 4. Reassess. We measure the change to prove the intervention worked.
And Step 5. AQ update. We confirm the numerical improvement and adjust the plan. It's a closed loop that ensures the training is maximally efficient.
Ultimately, understanding the error in ARES is about realizing the primary bottleneck in high-speed sports isn't the body, it's the brain's data pipeline.
We tend to assume our eyes guide our actions. We focus on what we consciously see. But in high-speed sports, it's actually the opposite, isn't it?
It is. It's your brain's learned ability to ignore 99% of what you see, to ruthlessly filter the noise that determines your speed.
So the provocative thought for you to take away is this. If elite performance is defined by how cleanly you route the critical signal, where is your system failing?
Are you slow because you see too little? Or are you actually slow because your brain is trying to route far too much?
Don't guess where your performance is breaking down. Get your AQ baseline.
Yeah.